All right, let's start with Ceph. So as I mentioned earlier, in Kubernetes, there is a set of persistent volume plugins which allow connecting to either standard like NFS or iSCSI. And for public clouds like Google, Amazon, Azure, you can use proprietary storage solutions, and those will be supported only inside their clouds. So you can request to mount to block storage in Google and basically get the block volume inside your pods. And it has some advantages. Their storage is highly durable. You won't lose your data. You can create snapshots. It provides a great performance, elasticity, so they take care of loads. It can be encrypted probably, and those volumes will be dynamically provisioned. You request one and you get one created in the cloud. But with that, provisioning might be slow in clouds. You will wait for some time until your volume is created. And the issue is that it's quite expensive compared to other options. Also, because their data centers are spread across multiple zones, you usually have your data in one zone and you cannot access it from the other zone. And of course, those solutions are proprietary, so if you use one, you cannot switch to another one. So your data is locked in that cloud. And the biggest issue for us, I guess, since we're discussing the kubeadm, is that those solutions will not be available if you create your own cluster. On the other side, Kubernetes supports local storage. You can access the nodes drives, and even public clouds provide that capability. So you can request access to local hard drives with low latency, and if you compare prices, it will be relatively inexpensive. Again, if you access local storage, there is no dynamic provisioning, and your data is tied to just one node where you're running. If you compare latency for public cloud storage, then it will be much higher than accessing the local drive, obviously. So this is plot which clearly shows the difference for two clouds. I think it's Google and Amazon on top, and then local NVMe drive on the bottom. List of volume options from Kubernetes documentation. You can see AWS, Azure, and Google. Yeah, GSE, persistent disk. Also, there is GlusterFS and some proprietary storage host, prop vSphere, and so on. But also there is a solution not included in Kubernetes documentation for some reason. They are now trying to become standard, and I think they making good progress on that. It's called RUK, and RUK is a wrapper for Ceph file system. So Ceph is, I think it's open source, right? Yeah, it's open source, developed in. Yeah. Oh, yeah. Recently became a part of Red Hat, so now I guess it got great support, and lots of big clusters are using Ceph. And Rook started from just supporting Ceph, and in recent version released 5 days ago, they also included support for 2 more NoSQL database and some other one. So they are extending the range of file systems they provide. But Rook is a great way to get persistent volume the same way you will have it in Google and Amazon, but on your own provisioned cluster. So basically, Rook will use your own drives for you and will provide the dynamic volumes. Out of the box, Rook provides block storage, object storage, compatible with S3, and shared file system. So difference between block volume and shared file system is that shared file system can be mounted in parallel to multiple pods. And for block volume, you can only mount it to one pod. And until, again, this recent version they released 5 days ago, file systems were broken. There was a bug in Ceph that was causing the whole file system crash, and we were not allowing users to use shared file systems. But now, once we update to the new version, we will support shared file systems, and users will become much more happy because they will create distributed workflows and use the same data. Rook can be hyperscale storage, which means that you just create a Kubernetes cluster, deploy Rook, and use it from somewhere else. Or hyperconverged, which means you both store your data in your Kubernetes cluster and compute and run your some workflows using this data in the same cluster. They claim zero-touch management. It's not 100% true, probably 99% true. It significantly simplifies the way you deal with Ceph, because Ceph has a bunch of tweaks and configuration, but Rook is makes it much easier to deploy a Ceph cluster. But later, like if you have to manage, you still need to do some Ceph management, but again, it's much easier than if you just create your own cluster, like pure Ceph cluster. Rook will make sure that your data is replicated. Again, you have controls over that. It's elastic, you can scale it, you just add more drives and it will scale up to petabytes. And runs on commodity hardware. You just throw all the nodes and all the drives you have at it, and it will spread on all the drives and make sure that it balances the speed and capacity in the right way. RUK architecture. This is again from RUK documentation. RUK cluster consists of monitors. Those are components that store the state for the whole cluster. They know where data is, how it's migrating, all the replicas, stuff like that. So you want to make sure that your monitors are consistent. So there is a special algorithm for reaching consensus. Each of them can die at any time, but as long as a couple of them are running and can talk to each other, your cluster is safe. And again, great thing about Kubernetes, it will make sure that the number of monitors required is always running. So when one of them dies, it will start it somewhere else. It will keep up with the rest of them. So it's very stable. So manager is another thing just for monitoring things, and you have a set of OSDs which control your drives, format them, put data on them. If drive dies, then it will make sure that it migrates data somewhere else and to keep the requested number of copies for your data. Also, OSDs scrub the data periodically to make sure that all is safe. So it takes care really of your data. On top of that, there is a layer that Rook provides. Each node is running an agent, and that's the component that mounts. So it basically deals with Ceph. That's just a wrapper for Ceph. When your pod is starting, you can directly mount Ceph volume, and that will go through agent. Or you can ask Kubernetes to create one for you and attach to your pod before starting. So Kubernetes will make sure that the volume is created, and then it will start your pod, and you will, once it starts, you already see your data inside. And to do that, you create what's called volume claim. So you claim a volume, and Kubernetes does all the magic. This is a scheme from March 1st, list of our Kubernetes nodes and how much storage we had at that point. We increased, probably doubled already the amount. So most storage we have in UCSD, KL82, and there's a bunch of others. So most nodes have NVMEs and SSDs. Some of them have 10 terabyte drives, and currently, okay, I'll show the Grafana. So this is monitoring. Can you see it? Okay, good. So now we have 700 terabytes total capacity. That data is 3 times replicated, so you divide it by 3 and you get how much data you can really store in that cluster. And the reason for 3 times replication, so it's 3 times replication, and there is also a parameter called mean size, and in our cluster it equals to 2, and that says how many copies should succeed for IO operation to succeed. So when you're writing a block of data into the cluster, until the cluster has 2 copies of your data, it will not return. So basically it will block. And third copy will create it after. So if we create just 1 copy of your data and this node dies, then you lose your just written data and data can become corrupted. At some point we had mean size set to 2 and also replication set to 2. And in that case, if one node dies, then writes stop until the cluster migrates this dead node somewhere else. So you cannot read or write until everything is migrated. And 3 is great because if one node dies, then cluster starts migrating data somewhere else for this third copy, but you still have 2 available and all IO operation continues. So once we have this scheme working, there are no stops in our cluster. So it's showing status is healthy, monitors in quorum 5. We are running 5 monitors, default is 3, but 5 is better. We can lose like 2 of them and still have a bunch working. Number of OSDs is number of drives across all the nodes. All of them are up, so all those green squares show that none of is down. Again, once one of them is down, it starts migrating data somewhere else, and we see it on this dashboard. So it shows supply latency for OSDs. It's close to optimal. 10 is when it gets green. And IOPS, so it's probably hard to see. Before this conference, we had close to 200, 300 megabytes per second rate. And now I guess everyone is happy and computed what they needed, so it dropped a little. Probably after the conference it will go up again. And those peaks reach, so this is for IOPS, this is for throughput. Here peaks reach about 500 megabytes. If I just do DD from dev 0, it will show around 2 gigabytes per second rate, which is pretty good. So we never saw it in real workflows, but that's, so we are not at the limit of throughput. And all those SSDs and VMEs allow us to really show a good throughput for the data. Any questions so far before I, yes? Yes, the cluster size doesn't matter. If we add additional storage nodes, yeah, we just add them to the cluster, and the data, like cluster will rearrange the whole scheme, and some data will appear on those new nodes. And so yeah, it's really scalable. So Ceph says that they can scale to tens of petabytes or even hundreds of petabytes. Yes. Yes. And yeah, they had it from the beginning, but in recent version they made some improvements, so you can use it for all the types of like file system, block devices. So that should work. Yes. Yes. Mm-hmm. It is not. In Ceph, there is a ability to create zones. And if you do that, you might do that also in Kubernetes nodes if you really care about it. In our cluster, we just spread it. So once you push your data in Ceph, it's everywhere. And because you have 3 copies, usually I think it starts reading from all 3, and the first one it gets is the right one. So the speed is really good. Slow nodes kind of keeping the data secure, but fast nodes will get your data fast. So we don't see any issues yet, but once we have, so our cluster is now international. We have node in Korea. Once we have more international nodes, I guess we might want to think about it and create like Asian pool, European pool. But for now, we are happy with what we have currently. More questions? Yes. So some nodes we manage ourselves. They belong to PRP, but they are located in different universities. Just recently, John Graham and Tom DeFanti made a trip around California and spread 10 terabyte boxes in those FIONA. Some organizations just provide nodes and they put storage in them, but they tell us which drives they give us. And those drives we say, okay, those drives Ceph can use. So it's we are very flexible, and like whatever is donated to this cluster it gets used. Yeah, so if people give us the root and the APMI, then we manage it, but basically we just reboot it when it hangs. If some people decide to do it themselves, then we just give them token to join the cluster and they do all the administrative part. So it's up to people. But all of them automatically get perfSONAR and Grafana monitoring on their nodes. So once they join, they get all the monitoring containers. Grid FTP, we are now working on it, so it's not part of cluster yet. There is no grid FTP in perfSONAR. I can answer this question. Oops, it's not the right one. So this is our perfSONAR dashboard for the Kubernetes cluster. This is a WOMP for all the nodes in the cluster. Big one. And then for throughput, we only do IPv3, not grid FTP. And those are separated to 100 gig, 40 gig, and 10 gig. And that's all we do in Kubernetes for now. There is a plan to do grid FTP, and we were actually waiting for this grid FTP plugin to become available because doing it manually is a pain. So now we can, together with IPv3, we can do grid FTP, and that's probably will be done in the next couple of months.
Right, yeah. So Alex, so there, in the run-up to this workshop, and through one of the other efforts that you'll hear about later this week, the NRP pilot, there's a student-led group out of the University of Michigan that had taken one of the wish list items for perfSONAR to develop a GridFTP plugin. And then that could fit within the pscheduler framework and take away much of the tedious work that we were trying to do in the last few days in the workshop here. So that's currently in kind of somewhere between alpha and beta. And we would expect that by the time of the Internet 2 TechX event in Orlando later this year, that would probably be available and be highlighted along with the 4.1 version release of the toolkit.
But that's for monitoring and testing.
Correct.
Some of them are used outside of Kubernetes for that. For containers, I already showed how it's easy to deploy a container that does just GridFTP. And for Globus, Nadia is now working on doing this stuff. I think once we have, so there is a plan to do MetalLB, which will provide the capability to announce an external IP for services. Because Globus requires a wide range of ports open, and we cannot. It's hard to do that without like this external IP capability. But once we have it done, then we will be able to create a Globus Connect endpoint, and then users will see their pods in Globus. But that's hopefully near future. More questions? Okay, so now I'll show how Rook is deployed in our production cluster. Rook is using two namespaces, Rook and Rook system. These are pods running in Rook namespace. Okay. First pod is API. Again, Rook is exposing REST API, and all the pods are using that to access Ceph. Manager, this is for external monitoring, and 5 monitors. So these are kept up, and once one is dead, then another one appears. So you see that the biggest one is 43 now, which means that it died already around 40 times. Yes. Per node. Yes, and the rest are OSDs. And so you can see the name of the node. Actually, I didn't show the... So this is our cluster nodes, all of them. We were, just before the conference, we were running experiment by extending the cluster onto Comet. So some nodes were running in virtual machines on Comet. These are not ready now, so they're shut down. Controller 0 is the master node, same as what we deployed today, but none of user pods are running on it. And then there is a bunch of other nodes, and if I can do... If I do -l-env, it will also show the label, and this is just label we did ourselves, but this allows separating the nodes by purpose and to map certain namespaces onto those labels. So we see production, and most production nodes are running Ceph storage. Then there are some CHCI nodes. This is node dedicated to a separate project. OSG nodes with stash cache. These are Internet 2. And so a couple more. So this is another OSG node. So basically, if we go here, we will see the nodes running the OSDs. And the last container is RUK tools. That's a client. So to access Ceph for admins and to see the monitoring for it, sometimes they develop their own tools container that gets all the credentials, like admin credentials for Ceph. And I will show it in a little bit. And also, if we do RUK system, let's also. So if I just do get pods, it shows basic information, but I can do also -o wide. It will show more information, including the IP and the node it's running on. And most of them are RUK agent. This is pod that serves as the layer between pods and Ceph. So basically, it will do all the management. In general, it just creates a RBD device on the node for Ceph. So it mounts the Ceph RBD device on the node and then tells Kubernetes, okay, here's the device for your pod. And then Kubernetes will use it when starting the pod. Some of them are, these commit nodes were disconnected, and so it's saying that node lost. So it remembers about the pod, but it's not active right now. And this is how many times the pod restarted. So some of them, if node get restarted or there are some problems with the node, then pod get restarted. And we can see the age of the pods and the current IP, which corresponds to the IP of the node itself. And this is really important pod operator. So operator in Kubernetes is a controller, usually a controller pod, which works close to the Kubernetes core, and it spawns other pods and manages like everything inside the Kubernetes. So first thing that RUK creates is this operator, and it basically creates everything else. And also it manages the things, like it watches the monitors, spawns another one, and so on. Okay, now we can go. So now I'm going to exec into RUK tools pod. Exec -it name of the pod and then namespace RUK. And we're executing bash in it. I can show the tree of all OSDs. So Ceph creates a tree structure, and we can divide it by regions, by data center, so on. But in our case, it's just a flat structure, so root and then nodes. And for each node, it has a list of OSDs, which correspond to the device. And Ceph will make sure that these three copies are spread on different nodes. So they will never be on the same node. We can also, if we divide it by data centers or regions or so on, we can request upper level of replication. So we can request that three copies are stored in different data centers, for example. So if network dies in one of them, you still have access to your data. It shows the type of the drive. You see SSDs, hard drives, some of them are NVMEs. Next column is the weight, and weight shows how much data you can store on this drive. So if it's small, if for smaller drives, it has smaller weight, and so it puts less data on it. For bigger drives, it puts more data, because otherwise small drives will be always 100% used, and bigger ones will not get any data. No, we don't. Yeah, that's, I guess, next step, but for now it's working great the way it is. Yeah, there was no tuning so far. It's just working. Yes. If we have network outage in SDSC, it will take out probably like 10 nodes at the same time. We saw it once. Yes, it happened. But other than that, sometimes Ceph, if there is a network connection problem, like network exists, but something is really wrong, then Ceph becomes unhappy, and this node can report that all other nodes are broken if this node still has connection to monitors. And I saw this happening a couple times, and then the whole cluster becomes, like half of the cluster becomes unresponsive. And I'm dealing with that by killing those pods and figuring out like which one should I kill. It happened a couple times, and it causes the outage for service. Probably yes. If I define data centers and I request that copies are stored in different data centers, probably. But again, if node reports that nodes in other data centers are not responsive, then it will probably cause the same thing. But yeah, I'm still learning Ceph, so I saw it a couple times, and I could deal with it, but I don't have a proper solution to that yet. Yeah. Yeah, there are a bunch of tweaks also. This is running default settings now, and I can probably increase this interval when node becomes out of the cluster, so that it doesn't immediately shut down other nodes. This is, I think, 12, and they just updated to 13. So in NRP cluster, I think we're running the newer one. But this is old, and update is after the conference. I didn't want to break it just before the conference. But yeah, Rook guys are really great. So when Ceph implements a new feature, they release a new Rook, and hopefully their upgrade guide will become better, because now it requires some manual intervention, but they are moving towards just killing the pod, and it starts the new with updated Ceph. So that would be really cool. Last columns are rewait, and this rewait is temporary shut down an OSD. And when I change either wait or rewait, it will start migrating data out of it. Okay, good. Okay, I have some cheats here. So I'll just touch it a little bit. For this last OSD 79, we can set a different weight. We can set it to 0.1, for example. And then if we do Ceph health detail, It will tell us what's happening in the cluster, and it will say that there are objects misplaced. Watch. So basically it's telling that there are all objects are fine in the cluster, but some of them are not in the place they are supposed to be. And it's moving them somewhere else. And because I changed the weight of one OSD, it now wants to move some data from this OSD somewhere else. And this is really great feature because all OSDs in the cluster interact with each other and they can achieve really big throughput. So when something breaks, you see like a couple gigabytes or tens of gigabytes per second when they are migrating data somewhere else. So it's really quickly fixing the problems in the cluster. And again, it's adjustable. I can say how many OSDs can do it at a time. If I want faster fix, I can say I want more OSDs to migrate data. If it's just small problem and I don't want really to Ceph to like suddenly migrate all the data, then right now I think I have 2 OSDs at a time migrating, so it's not that fast. But that's because a couple months it was very stable, and so I don't want big changes in the cluster. So now I will change it back to 1. We can see again in the tree that it returned to 1. And if I do health again, it was finishing that migration and now it's showing health okay, which means that nothing is happening and everything is happy. So there is a Ceph -w shows what's going on in the cluster IO stats. How many, so we have one big pool for all the data, how many objects we have, so that's how all the files are divided in the cluster, how many gigabytes, I don't know, we have 32 gigabytes of, I don't know what that means, but yeah, so we have 700 terabytes available. And placement groups is a small block where it stores the data, so it has 2,500 placement groups in the cluster, and it's moving data by placement groups usually. Also 5 monitors, which are in consensus. Okay, so how do we request persistent volumes? And I will show it on the example of perfSONAR. When we deploy perfSONAR, the only state we want to store is Cassandra and Postgres database. Everything else is stateless in the cluster, because test points just get configuration from central MA and they don't want to store it for a long time. They are dynamic, and central MA wants to store the history. This is pod for Cassandra. As I said, it's a stateful set, which means that we have n replicas and they have a certain name. So they always start up with a name. We're using Google Cassandra pod. And in the end of the definition, we create volume claim template. We say that we want, it's called Cassandra data. We are using RUK block storage class. And each Cassandra instance gets 50 gigabyte storage. And in Ceph, it's really easy to increase the size of the volume. So I started with 50 gigabytes. I think I increased it to 200 gigabytes per pod now. Also, if I add more Cassandras, we will expand the storage, but that's what it's defined here. And for these volume claim templates, we create volumes. So, volumes is another type. So there is one empty dir and one config map. But this Cassandra data is mounted in /Cassandra data inside the pod. So basically when pod starts, it already sees this persistent storage. And when they restart, they just keep from the point where they shut down at. And for perfSONAR toolkit itself, its deployment, as I said, and there is a persistent volume claim for it, 100 gig, which is a plenty for Postgres database. And it gets mounted, let's see, yeah, here. So just directly Postgres gets this volume. And so on first start, if this folder doesn't exist, then init script runs that initializes the Postgres database for perfSONAR. And on next starts, if it sees this folder, it just continues working. So everything else is dynamic, all test points and everything else. Now, yeah, we have 5 minutes. I can answer questions, or I can show how to deploy Rook, like some YAML files. No questions. Okay, let's. So there is a Rook folder. On that page, there are links to GitLab repo, and you can see all the config, but these are pretty much taken from Rook documentation. So this is CRD, cluster resource definition. This is extension to Kubernetes API. So Rook creates its own objects in Kubernetes called cluster. And for this cluster, they define which fields in YAML they can specify. And for Rook, it's store type, blue store. So this is most the recent store for Ceph. And then we can say just go to all the nodes and grab all the drives you can. It will do that. But in our case, we want to carefully specify all the drives for every single node in the cluster. And that's how we do it. So there's for every node, we say which drive gets initialized. And I can, yeah, these are broken ones. For new nodes, we can, there is already object in the Kubernetes cluster, but we can edit it and Rook will see the changes. And if we add another node, it will add this node to the cluster dynamically. So it will change the Ceph crash map. And also if we delete a node, it will delete it from the crash map. Unfortunately, it cannot delete a single drive or add a single drive yet. So if I want to add another drive, I have to delete the whole node, wait for it to migrate data out of it, and then add it with another drive, and it will migrate data back to it. And once we created this cluster, I'm sorry, first we create the operator. That's the pod I was showing. So it's Rook pod. And this will create the operator. And after it, we create a cluster. And when operator sees another cluster object appearing, it will create all the pods and all the stuff for it. So in theory, we can have several clusters defined just by this YAML definition. So it will create several Ceph pools and several clusters and so on, and they can be separated from each other for different namespaces. And the last thing you deploy is a pool. So it specifies, by default it's using Rook cluster, but we can say which cluster we create pool in, and RBD is the default name for pool. So here we say it's replicated to, yeah, I changed it later. So this is a way to create a Azure coded pool instead of replicated. So if we uncomment this, then it will create a Azure coded pool. And storage class is the way for pods to specify which storage they are using. So if they want, for example, if you deploy to Google, by specifying storage class, you can request either Google storage or Rook storage. And here you can also say that you want XFS file system. That's pretty much it. This service monitor is for monitoring. We're using Prometheus operator in Kubernetes cluster. And for every object that we want to watch, we have to create a service monitor. So that's a separate probably talk how we do it, but this creates one for Rook. And that's how this dashboard is working. I think it's... Yeah.
So questions for Dima? Yes.
Mm-hmm.
Different file system for every Cassandra node.
Yes.
Do you have any thoughts on creating a very large global file system across all the nodes versus creating smaller file systems like you did for the Cassandra?
Creating one file system will require this shared file system. It has a problem of decreased performance because it's shared. And there is not big benefit of doing that because different Cassandra instances cannot share the data, as I know. So this really, I mean, this works great for Cassandra. They just, each Cassandra gets its own block volume and works with it.
But since there's no locality in the allocation of the block storage in Ceph to the nodes, wouldn't you be better off just leveraging the local storage?
Oh, you mean local?
For each of the Cassandra nodes instead of using Ceph for having a POSIX, but then that data could be somewhere else.
Yeah, I was actually thinking about that because when we have network problems and Rook is not responsive, then we lose also perfSONAR. And so once we have problems, we cannot monitor problems. That was the problem. The issue with that is that if node dies and starts somewhere else, then this Cassandra instance will have to pull all the data in. It's not a big problem, but so far seems like it's a manual process. I know if you know enough about Cassandra, you can probably say if no, okay. Yeah, for now, what I see is that sometimes I need to go on the nodes and manually trigger repair, especially after they've been down for a while. And I'm not sure if they can, it seems like they can recover if they've been down for less than 3 hours. If it's more than 3 hours, then it's manual process. And I don't really like that. And I'm not sure how long it will take the full node to pull data. Because now every single node stores about 30 gigabytes of data. So it will probably take some time. But that might be a better approach in terms of being up when Rook is down. That's another way to do it, yes.
Great. Other questions for Dima? Okay, thanks, Dima.